In this video, we're going to be looking at three different types of series, and these are sort of the special types. First off, we're going to look at telescoping series, then we're going to take a look at geometric series, and finally we'll take a look at p-series. Okay, so we remember that an infinite series is really just taking an infinite collection of numbers and you are adding them all up. We very much want to know what happens to this infinitely long summation. Okay, as the number of terms continues to grow, does the actual sum itself, does the actual number continue to increase without bound, or does it converge, does it approach some finite number? So here, let's take a look at telescoping series, and we're going to jump right into an example. We want to show that this series is convergent, and then we're going to find its sum. So we are looking at this series here, the sum of 1 over n times n plus 1. We know from the last section that if we want to talk about convergence or divergence of the series itself, then we have this relationship. So here we can remember that the sum of a series can be found by looking at the limit of its partial sums, where capital N is the number of terms being added up in the partial sum, and then we can take the limit as the number of terms being added up approaches infinity. So this is very much what we would like to use. However, the real question and the difficulty for something like this comes from finding this partial sum. Okay, what is the partial sum going to be? And specifically, what is a pattern that will always or can always be used to represent the nth partial sum? Okay, so for this one, we can say that yes, our nth partial sum, it's going to be the sum starting at 1, and I'm adding up capital N terms, and the terms being added up are defined by this pattern. So this is my nth partial sum, and the very first term in this sum is going to be corresponding to our counter, little n, being equal to 1. So that's going to be 1 over 1 multiplied by n plus 1, which is 2. And that's going to be my first term. Really, that's a1. Okay, if you wanted to, that's your a1 term. Now, fine. Let's take a look at a2. So if my counter itself is at 2, then I have 1 over 2 multiplied by 2 plus 1, which is going to be 3. And I can keep doing this. Okay, my next term would be 1 over 3 times 4. And I keep doing this all the way up until we get to the last term, which corresponds to capital N. Okay, and the very last term here will be divided by capital N multiplied by capital N plus 1. Okay, so that's where we end our partial sum, and this is very much what our nth partial sum would be. Okay, and then you'll notice again, we're interested in knowing what happens here as capital N approaches infinity. And so if I look at my partial sum, what happens here as capital N approaches infinity? Well, this is sort of a problem. This is a very unfamiliar limit for us. We get, how each of these terms is going to be calculated. However, what happens over here as capital N goes to infinity? Well, those terms go to 0, so that makes sense. The terms being added up are getting smaller and smaller and smaller. They go to 0, but the real problem is that what's happening to the number of terms being added up? Okay, as capital N goes to infinity, the number of terms being added up is actually going to infinity. So we end up with a very familiar problem at this point, okay, in that we have the number of terms being added up is approaching infinity, but we're multiplying that essentially by 0 because each of those terms is going to be themselves getting infinitely small. And this should sort of remind you guys of that indeterminate form, okay, that struggle between infinity and something being infinitesimally small. Okay, what ends up happening? Does this series actually converge? Does it diverge? Okay, so that's very much what we want to do here, and we can't look at it in this current state of our partial sum, we need to find a more concise way of representing our partial sum so that we can actually deal with that indeterminate form. So what does that more concise form actually represent? Well, let's specifically look at the terms being added up. The terms being added up are 1 over n times n plus 1. Okay, now this type of function, this type of term should remind you very much of something. And the hint that I'm going to sort of give you is, what if we were integrating something like this? Okay, so off to the side, what if I was integrating 1 over x times x plus 1 dx? How would I go about integrating that term? Okay, what's the technique that you would use? Think about it for a moment. You can't simplify it. Okay, you can't really do a substitution. But what can you do is that you can do partial fraction decomposition. So we could do partial fraction decomposition on an integral, but we remember that partial fraction decomposition is not really just a technique for integration. It's actually just an algebraic technique similar to factoring. We can use it to simplify any rational function. So specifically, what we're going to do now is we're going to use it to simplify this rational function. This rational term here, 1 over n times n plus 1, what happens to it if we do partial fraction decomposition? We'll end up with two terms, 1 divided by n, 1 divided by n plus 1, and in the numerator we will have a and we will have b. So let's find a and b, and we can do that by just expanding and multiplying the right hand side here by this denominator, n times n plus 1. So let's cancel that out. We end up with it over here, n times n plus 1. So let's see what we actually end up getting here. On the left-hand side, we end up with just the number 1, our numerator. And on the right-hand side, we have a multiplied by n plus 1 plus b multiplied by n. And now we want to solve for a and b by just subbing in nice values of n. First off, we can let n be equal to 0, and then we get 1 is equal to a times 1. Really, we just get that a is equal to positive 1. And we can look at this term. What happens if n is equal to minus 1? And we get that 1 is equal to b multiplied by minus 1, which means that b itself is equal to minus 1. Okay, and so we have a and b, which means we could go back to our series. And our series, which was originally the sum of 1 over n times n plus 1, can now be broken up. It can be decomposed into this difference. I would have 1 over n minus 1 over n plus 1. And now that definitely at first doesn't look like it's going to help us, okay? But this is where the term telescoping is going to become important, okay? So remember, for this section, we are specifically looking at telescoping series, okay? And this is where we're going to understand what is meant by that name, okay? What does it mean to have a series that is telescoping? Okay, and the idea of telescoping here is we're sort of thinking of a very old school telescope, okay, one that sort of expands and contracts. So this is sort of the idea here, is that you can sort of increase the size of this telescope, or you can sort of contract it back on itself. Okay, so what we're going to look at when we do our partial sums is we're going to have a similar behavior. We're going to start out with a ton of sums, and we're going to be able to greatly simplify it, and we're going to be able to do so because of the way that this decomposition happened. So let's take a look at how that works. Here we're going to want to be looking at our partial sum. So we have s sub n. What is s sub n going to be equal to? Well, it's the first of, or the sum of the first n terms. So now if we look at it like this, if our counter begins at 1, then the first term being added up is simply going to be 1 over 1 minus 1 over n plus 1, which will be 1 over 2. That's the first term. That corresponds to our counter being equal to 1. Now let's look at the second term. If n is equal to 2, we end up with 1 over 2 minus 1 over 3. And I'm going to be using brackets here just to sort of keep the terms separate from each other. Let's take a look at the third one. What happens if n is equal to 3? So now we have 1 over 3 minus 1 over 4. And I want to keep doing this essentially until the pattern is going to be clear. Now that should be enough terms to start off with, but also we remember that this is the partial sum, okay? This is not the infinite complete series yet, so this summation actually does end. So let's actually just go down here and let's look at the tail of this partial sum. Let's look at the last few terms in the partial sum, and specifically let's look at the last 3 terms. Okay, and I'm going to start off here with the very last term. Okay, I find it a little bit easier to structure it in that way. So where do I stop? How do I know what that last term is going to be? Well, remember that this is the capital Nth partial sum, which means that we are going to be looking at our counter going from 1 to 2 to 3, but we're going to be stopping when that counter reaches the value of capital N, which means that the second last term will correspond to capital N minus 1, and the third last term will be capital N minus 2. So now that we have those set up, let's actually see what the terms themselves are. So if our counter is capital N, then looking at this right here, our last term is just going to be 1 over capital N minus 1 over capital N plus 1. Okay, we know how that pattern works. So then going to N, our counter being equal to capital N minus 1, we have 1 over capital N minus 1 minus 1 over capital N minus 2. Or rather, that's not right. It should be here capital N itself. We go to our counter being capital N minus 2. And now we have 1 over capital N minus 2 minus 1 over capital N minus 1. So now we have the first 3 terms and we have the last 3 terms, and we want to figure out some way of telescoping this. Okay, we want to figure out some way of taking all of these terms and getting rid of almost all of them. Okay, so I want you to look at this summation. Okay, think about how can you clean this up? How can you simplify this summation so that we can find a nice pattern for our partial sum S sub capital N. So here, you may notice that a lot of these terms just directly cancel each other out. So for example, if I look here at this negative 1/2, in the very next set of brackets, I have a positive 1/2. So I could definitely just cancel those terms with each other. And that's not just a coincidence. If I look at this term, I have negative 1/3 and I have positive 1/3. Those terms are also going to cancel with each other. Now, what's going to happen here with this negative 1 over 4? Well, in theory, it would have canceled off here with the positive 1 over 4 that would come next. So let's also assume that that term has been canceled. Now let's go to the last 3 terms in our partial sum and see what happens with our cancellation there. And for this one, let's actually just start off in the reversed order, okay? So I have here 1 over n. It's going to cancel with the previous term of negative 1 over n, so they're gone. This term, 1 over n minus 1, will cancel with negative 1 over n minus 1. This term would cancel with the term that would come right before it if we had written it, so it is gone as well. And that leaves us really with only 2 things left to consider. What happens to this term and what happens to this term at the end. So let's look at the way that these terms were canceling, okay, the actual pattern that was involved, and we'll notice that the second term in each set of brackets canceled with the first term in the next set of brackets, which means that this term that we started off with would have canceled with the term right before it, but unfortunately it's the first term, so this term doesn't go anywhere. Okay, it's one of the few that will remain. What happens here at the end? Well, again, what's our pattern is that the second term in the bracket cancels with the first term in the next bracket, so this one would have canceled with the next term, but because that's where we stopped our partial sum, this term does not cancel. Okay, so those are the only two terms that are going to remain at the end. And really, we can then rewrite our partial sum. S sub n is actually just going to simplify to leave us with 1, which is our first term here, minus 1 over capital N plus 1, which is our very last term from here. And now we have a much nicer, a much simpler formula for our partial sum than anything we've used before. And so now if I want to know what happens with my infinite series, all I have to do is check what happens here as the number of terms in this partial sum goes to infinity. Okay, what is this going to be equal to? And this limit is actually going to be very straightforward. We have just the limit as capital N goes to infinity. We're doing 1 minus 1 over capital N plus 1. And this term goes to 0. So all we end up with is 1. And that is the limit of our partial sum. So for this one, we would say that therefore, our infinite series, starting at 1 and going to infinity, of 1 over n times n plus 1, this is equal to 1, and it is convergent. So that is the first example of a telescoping series that we have seen. And again, the telescoping series effect is very much what happened right here, okay? When all of these terms sort of canceled out, leaving us with only 2 terms, okay, for our partial sum. That is that telescoping effect, and that's what allowed us to do this limit in a very straightforward way to determine whether our series converges or diverges. Now, one of the things that you will be looking for, and you'll often see with telescoping sums, is this partial fraction decomposition. Okay, but it's not the only scenario where you could run into a telescoping series. All right, what we're going to look at in the next example is something slightly different, but we do end up with that exact same telescoping effect, but for a slightly different reason. It's not going to be there as a result of doing a partial fraction decomposition.